is my doctoral from State University in electrical engineering. And my specific focus on video computation, specifically the discussion visibility models. So I will present a database specifically for natural scenes, which is the largest right now. And the total purpose and process was to get a data set, and then from sciences perspective, we actually observe what's going on with the data set, and try to, as we have a newer data set, definitely we have to have a computational model. So I'll talk about specifically 3 models over here, and how these models are connected with my brain and some of my hypotheses and suggestions, and then some of the applications for the engineers certainly. Yes, so let's start now. Would you mind monopolizing visibility? So, as you know that recently, machine learning and artificial intelligence, specifically the machine learning part has improved a lot because of the deep networks, as I said. And the cognitive computing it's a little bit vague term, because I mean, you can see a lot of people from a lot of different disciplines are coming on. If I'm going to say more, probably I'm coming out of space with this slide. So I put some of the important parts of it. But if you think about the goal and the knowledge that we are having from these studies from the academia and from the industry and from independent researchers, it's some of the parties definitely understanding the operation of the brain, or probably by the byproduct of the knowledge that comes from the training algorithms or any kind of algorithm, that we can see that those are mimicking some mechanisms of our biological brain and the memory of brain itself. Now, our brains functions that definitely we can divide it in many parts, but from very top level division that we can say is perception, that is understanding what is what of the environment. Definitely the cognition, hierarchical thinking that comes in reasoning for the small connectivity AI, and action, which is actually creates the experience of what we do using our perception, using our cognition. Now these are vast fields. Each one of them can be, you can work for whole life. But what part I'm going to focus on, I'm going to specifically focus on perception that we here work on. More specifically, perception can be speech perception, audio perception, vision, touch, smell, anything. But my focus was visual perception specifically. And visual perceptions, within the visual perceptions, my focus was specifically, it's called visual masking. I will show you. If you know, then I will show what's very useful. And how high level recognitions actually may affect the visual masking, which is generally known that it's low level vision phenomena, and some biological possibility of this that work on. At the end of this talk, if you come out with the main focus of says intercortical feedback, certainly is everything in the brain technique. But how do you actually computationally model efficiently this feedback so that we better model and better methods? So there's a big focus. So Here I'm going to show what was there. Here we see an image which is a reference image. It's a very beautiful image. It's distorted with DCD distortion. Now, if you see, it's very much visible, the distortion over here. It's a little bit difficult to see the lesson. Not difficult, but less visible within the various regions, right? Now, you can think that it's very much easy because for this it has high frequency components more. So it's probably having more distortions over here. But there are not much more. So I'll show you later. So if I take this image, divide it into several specific blocks, then ask human being in an experiment which part actually hides how much distortion, or what is the distortion, lowest amount of distortion that you just begin to see. There's a threshold amount of distortion. Then we get this kind of map, and I call it a masking map. So each region within this image is showing how much distortion can be hidden within this specific location where it just will be distortion. So more masking means it can hide more distortion, less masking means it can hide less distortion. Now, to give you an idea about the end application, what can be the end application, it can be a compression, for example. Generally, the encoder will give you this small file size of the video. However, if we have an accurate prediction of this map, we can use this map to allocate bits where more bits can be given or where less bits can be assigned to have better similar quality computation, but you gain some bits, less amount of bits. There are some other applications like picture analysis, quality assessment, watermarking. Now, the flow of my talk will be three parts. One, first is the data set that I'm going to talk about. Second is the computational modeling. There will be three computational models that I will explain. And third is the application the future flow. Let's look at the data set. So traditional stimuli. So by stimulus that we mean that a signal that is shown to a human subject within the experiment. Well, in our experiment, in my experiment specifically, it was a visual stimuli. This is a vision experiment. If it's an audio experiment, it can be an audio stimulus as well. So in a masking experiment specifically, we have a stimulus which is built of two parts. One is mask, one is target. You can think mask is an image, that's an image, and target is the distortion itself. So we put a distortion within the image and try to understand how much distortion can be put there where we just need to see the distortion. So there's the goal. Now, traditional masking experiments generally have very well-structured masks that we call unnatural masks. So if you see sound vibrating, visual noise, checkerboards, yellow pattern, the pro of this kind of mask or target or stimulus is that we know the specific frequency orientation, that in this structure, we know the signal very well, and we can regenerate the signal very well. But the con is that it does not have any recognizable pattern, right, as the natural scene would have, like faces, like hands or feathers that we can recognize. And more importantly, our human brain, its response is nonlinear. So given that two signals and the output is not a linear system, we cannot say specifically that given a natural scene, using the unnatural stimulus's result we can actually predict the natural synthesis better because our visual system is not linear system. So for these regions, and as we have natural scenes mostly available for executions, it's very much important that we created a set. So our stimuli specifically was the mask came from the natural scenes, specifically the small blocks from natural scenes, and the target came from a log-given mask. So the difference was that the mask was coming from natural scenes, and the target was coming from a unnatural signal. Now, why is this signal? I will explain later. Why is this log-given noise specifically chosen for this experiment as the target of the distortion? Now, if we add these two signals, then you see we can see the distortion within the region, right? And if you see the stimulus specifically, the edges of this distortion has been merged at the size of the image so that it's less edge effect is there. Similarly, some part of this extra part has been padded so that it gives some local effect during the experiment. In the subtent angle, that means that the stimulus that the subjects will see during the experiment within the dark room, it is 2 degrees of angle, and the reason that we show the 2 degrees of angle because in our phobia, the central foveal angle is 2 degrees, so to ensure that it does not go beyond that limit, we show this region. Now, if you see the contrast of this target has been decreased in this slide, so it's still visible. Now, we can decrease it more, and it's not too much visible. So the target of our experiment is to find the specific contrast of the target where we just bring this distortion. And at that point, we measure the contrast detection threshold. This is what the significant. So I'm going to show the metric that we use to measure the contrast detection threshold. That's called the RMS contrast. It's a very well-known metric to measure the distortion visibility. If you see this equation, log 10 of sigma t divided by mu m, sigma t is what? It's standard deviation, right? Standard deviation of the target of the distortion. And it will essentially measure the ripples within the distortion very well. And with respect to the average luminance of the mask of the image. So we know that how much ripples within the signal is responsible to give us the lowest amount of distortion that we just see. Now, procedure was sort of the psychophysical procedure, 3 alternative force choice experiment, and room and state. We have increased the resolution of 14-bit using a displacement device. And we had a total 1,000 HS. It's about this still now. And it's actually a very time-consuming experiment. That's why we had 6 measures per patch, using 3 subjects and 2 runs per subject. And subjects were very consistent. If you see the intra-subject relation coefficients, it's every time very consistent. Now, as I said before, that show why did we choose this specific target. You see that we chose the target so that it has around 4 cycles per degree, and the reason is that in our visual system, the peak sensitivity occurs at 4 cycles per degree. So we wanted to have the peak distortion to come into our visual system to get the maximum output that we can get from this experiment. And why is this vertical orientation? Well, we know that our visual system is more susceptible and more, we can see more of the vertical structures or the horizontal structure because from the evolutionary perspective rather than the oblique angles, the plus minus 45 degree angles. And to generate this signal, we chose a uniform symptom noise in the low-level filtering. the frequency response and equal this signal. Now, the masks came from these natural scenes, and you can see these scenes came from 6 categories: landscape, plant, animal, people, structure, and urban. If you see from the top to bottom, we are increasing not the complexity, we are adding more and more man-made structures. So from top to bottom, we are actually adding more and more recognizable structures or man-made structures over here. And which came from the CC dataset. So totally we have 40 scenes, and for each natural scene, we picked 36 patches, so altogether 1,000 patches. Now I'm going to show the results of the experiment with the dataset. The results of this, the dataset has been shown in terms of masking map. So at the left, I'm showing one category from the landscape category, the sunset color image. On the right, the heat map has been overlaid over the scene to get more visibility of what's going on locally. In the top middle, we are watching the average of these six measurements that we have for the 3 subjects. And left and right, you can see the one standard deviation up and down signal. You see that one standard deviation up and down is not too much different. So the standard deviation comes from the different subjects' results. And on the right, I'm showing the color bar. So red means no masking and blue means masking. There are several parts that are into two specific phenomenon I want to show over here. If you see within the sky, there's not too much textures, so there are some variations within the sky. And over here, where it's too dark, we're having very high pressures. Now, the reason is specifically called zero frequency masking. So when it's too dark, we actually, no matter how much distortion we put, it's going to come dark, right? And so when it's dark, we really cannot see any distortion over there. So if the neural noise and increase neural noise is going to hide all the distortion put over there. So that's why we are getting too much high masking over here. And other part is that I'm not sure that for that. See that we have some masking going over here. This masking is over there. But what's happening over here at the edges? We can see this edge has very high contrast, right? And generally, what happens, we know from the traditional studies, that traditional masking study, that if it's high contrast, it's more masking. So it should go up. Rather than going out, it's going very low. So the reason is that it's actually called cross-orientation facilitation. The reason is that when we put the distortion over here, if you remember, the distortion was vertically oriented. So if the distortion is vertically oriented, these regions, which are more horizontal, simple edges and very high contrast, they're going to help to see the distortion rather than hiding the distortion. So that's the process we call the facilitation, specifically cross-orientation facilitation that we observe over there. Second image is a category from animal. It's gecko city. In this sand region where it's very much noisy and not noisy, high frequency over here. We usually have very high masking going on. But if you see in these gecko's bodies, well, it also have high contrast. So it should have higher masking. But rather than that, we're having lower masking. So the reason that it's happening is called structural masking or entropy masking. And that's the part that we're never going to have without natural masks. Because during the experiment, subject know that it's a part of a structure. So if there's a structure, it is going to have different type of masking rather than a just purely, for example, sine wave or Galois pattern. So these structure matters. So then we can draw differently from this experiment. And third category that I'm showing is sample volume. If you can different other images have different kind of effects. Now, right now I've talked about the experiment, and we had several observations within from the experiment of the data set, but that experiment is very much time consuming, right? So we want to have a very much powerful and computationally efficient model to have a prediction model. Now I'm going to talk about three specific models that I worked on. One is the feature-based model. The second is the gain control model, and I will do convolutional-neural-network model. And at the end, I'm going to show where actually these models fail, and why is this failing, and do we have anything to make it better. Now, for the first model, it's generally a regression-based model. But before going to a regression-based model, before showing the results of the regression-based model, I'm going to show you the individual features. If we choose individual features of the image and try to predict the distortion visibility using the feature of the image, how do they perform? If you see that I have chosen several features, and the feature is specifically the contrast, the microscopic contrast, the RMS contrast, it is mostly used right now to predict the distortion visibility. It is very much used in this algorithm right now, the algorithm that we have. If you see the correlation coefficients, it's coming only 0.5. Sounds so good. And also some other features, you see band energy, local entropy, they are also not being so good. We found that rather than those features, sharpness is doing pretty good at 0.7. That knowledge was not known previously. So sharpness within the natural scenes have really deeper effect to understand the distortion visibility of masking rather than the known features of the contrast of the standard deviations. Now, definitely, if we use a regression-based model of nonlinear feature regression, see the testing data, and there is all data that we have, the 1080 HS, and 15% test data, all the image that we kept separate from all the data in the training process. You see the correlation coefficients coming from 79 in all of the data, and finally to even the test data. There are a few points it's not doing this so good. For example, over here, where the images is very dark and very high masking going on. And over here, there are some points it's not doing so good. Now, the features that I told you, it sounds very good, but the sharpness feature, it's not so easy to compute. And most importantly, if we want to build a very fast model, computationally fast model, the feature that I've told you is very computationally complex to compute some of the features, and it takes a lot of time for the computation. So this model, although have a fairly good performance, it's not fast enough to build up to put in an actual algorithm for the critical purposes. Now the second model that I'm going to talk about is the gain control model. So the gain control model will take two inputs, one the mask and the mask plus target. The mask is directly the image, and mask plus target is the distorted image. And the gain control model will give us the output that the minimum contrast of the distortion that is required to predict the distortion visibility. Now, this model that I'm going to show is specifically the Watson-Solomon model. It's really good as far as the biological plausible model can go. And this Watson-Solomon gain control model specifically designs the one simple sense model. So I'm going to talk about some part of it. You see, both the mask and the mask plus target go through a similar process. the contrast sensitivity with the CSF, then log-level decomposition. Excitatory normality, that's single cells excitations, the firing neurons. And the dividation process is mainly the gain control process that goes on. Well, we can talk about, we can tell the excitatory normality has a single neuron cell firing that's going on. However, there are several other neurons that are trying to inhibit the response of a single neuron. So the inhibitory pool is going to trying to inhibit the response of that signal. So we by the dividing process. And then we subtract the two responses, and these are as the before the dividation. After the dividation, we get these two signals, and we pull the two subtracted signals, and then we try to through an iterative procedure. You can see at the top, the iteration goes on, and we try to have the measured deep time as the threshold that we say, to measure to be equal to the predetermined threshold. And once we get very equality to values, then we calculate the final thresholds. Well, this model actually takes into consideration the V1 sequences model very good. But in terms of practical application, the cons that is, I would say, is the iteration. First of all, because the iteration takes a lot of time. And second is that once we do the log-level decomposition, better than administrative memory trace. So that's another memory issue. So, but it's a very biological plausible model. Now, the R, the signal, the neural network that I say, for each neuron, which is for a specific location, it's not one of specific orientation to another specific frequency. If not, the signal can be shown in terms of the division process, that the excitation and the numerator and the inhibition process relate to the denominator. And this specific term is the inhibition that's coming from the close by neurons in different orientation frequency. And the G prime, there's the mean pulling going on. And the inhibition, that part is still a little bit difficult to say. How far do we go to the frequency domain? How far do we go to the orientation domain? Or how far do we go to the space domain to have a better model? The inhibition, that's the term that will show that it matters today. So in terms of modeling, we chose three parameters. Was here there's the inhibitory exponent, and the overall output gain G, and the frequency channel bandwidth, we have left that actually. And the ranges that I chose to look into to do this model was chosen from very biological plausible before previous studies has used electrophysical studies, and neurophysical studies have the ranges that scientists think that they are biologically plausible ranges, and look into their regions. And instead of doing a regular optimizer, I chose the brute force method. The reason is that if I change the bandwidth specifically, frequency bandwidth, then my data dimensionality changes. That means the number of space that we use, we have to change it to make sure that the whole frequency spectrum is covered. And that's why to use the regular optimizer is difficult and brute force is easier. And if you see, the optimum ranges are within the range. And specifically, these frequency channel bandwidth are a little bit higher range rather than the electrophysical studies found before. But I think it's coming because of the natural scenes that we see. Some of it has different ranges of frequency ranges, and they have spatial correlation in the signal, and they have different effects. And that's why my ranges are a little bit in the upper range than the physical studies, but it's still within the range. So that's good to know. The results, if you can see, Here it's more compact than the previous feature-based model. There are some points that we see is going beyond very far from the 45 degree point. And in fact, the looping square error and the Pearson coefficient that we find in this game control model is the best among the three models that we found. So now I'm going to show the third model, the convolutional-neural-network model. The purpose of this model, why did we try this one? Even we have a game control model. Twofold. First of all is that if we have a kernel that's going to predict the instruction result really well, we can parallelize it. It's a convolutional operation, so it's going to be faster. So it's going to be very much applicable in if we see the coming HPC computational algorithms is going to be very effective in terms of computational complexity and computational faster. And second is that we also don't know some features. What's going on within the images that's giving me the results. That's why we tried this one, and we did not try a deep network. It's a shallow network. So only has three layers. And sure enough, we don't know how big the kernel should we have to get a better prediction of the process kernel. And we found that 19 by 19 in this software, you can see 19 by 19 dimension kernel, x and y axis. And it has pretty good performance in terms of the square error. And we used a 50 network, we trained 50 network individually and took the outputs, average output to get that output. Now, if you see the trained kernels, here at the left top, I'm showing you the kernel. The left top is the kernel that gives the best results. And the right bottom, we have the kernel that also from the feature. So what does it do? What do we do? If we do a convolution, just compare the colors of two spots. We don't have any color in this one. It's totally meaningless. It's just two dot, right? And if it's two dot, if you see three-dimensionally, it's one vertical and one right at the top of the bottom. It's going to find horizontally vertical. That's right. So it's vertical. Mostly vertical. Yes, mostly. Yeah. It's that. And I'm showing you
ask questions along the way, or do you want us to save it all to the end?
It's okay.
I was just curious if you go back one page. Yeah. I'm just curious why 19 by 19 kernels were so much better than smaller ones. It looks like the kernels don't have to be that large to do what they're doing.
Specifically, they do have some other jobs over here. I'm showing you the logsters to get the best one. They do have some other jobs over here. And as I said, honestly speaking, I also don't know for the 19 by 19 really work, but I tried from few to really kernels that
Probably relates to the resolution of the
exactly.
Like the resolution of the
The other reason that I think that if we use the, for example, 3.7 cycles per degree, the cycle has to complete to get a total. For example, if we don't have a full peak of the distortion within the image to get the distortion visibility. For example, if we have a sine wave, if you want to put a sine wave in something. But if you have a very small part, we actually don't know, is it flat, is it just a signal, or is it a full cycle? So if we don't have a bigger part within the kernel, we don't know how much variability should we consider within the image together. Another part could be, definitely I'm sure that if you see that our distortion had only 3.7 cycles per degree, there's 4 cycles per degree, but sure enough, if I use some other frequency, it's going to change. So, but we try to be consistent with one frequency so that if we want to extrapolate with some other frequency orientation, we can do that. So it's pulling out mostly the vertical, yes, and for the energy is important finding the distortion for given the distortion that we chose to experiment. Now the results is showing over here. You see there's a significant thing going on over here, right? Other than the previous two models now. It's unfortunate that it's doing the clipping, but it's not unexplainable. It's explainable. Think about the convolution operation. If we don't have a pattern where these signals over here, where it's mostly dark, right? Dark that is the constant. If it doesn't have any pattern, so what if we convolve with the kernel, what are we going to get? We're not going to get anything. So if it doesn't have any pattern, too much pattern variability, a convolutional neural network might not get too much information from this image to predict the distortion visibility very well. So there is some explanation. See some explanation. Why is it not good? The correlation coefficient is 0.7, not bad, but it's a bit. The point that I'm going to show you is very fast. It's 20 times faster than the control model, and the time that I'm showing, the 5 seconds for a 10 by 5 10 gauge, 5 by 5 gauge, it's not using liquid or not using GP acceleration. However, the gain control model, which is, if you see the RMSC is 5.2 and 5.5, so it's very small difference within the models. However, it's really fast, and you can use it for doing faster algorithm. So, as we see that we know the models and completely, we know that how they are performing in terms of computational complexity and in terms of accuracy. The important thing to know where these models are failing. So that was the effects of information that we had where these models are failing. So here, you see the transfer unit. It has a very complex structure type. So, the experimental masking map, if you see, it's showing some development. This must be over here, the blue region. My feature-based model is doing good over here, something over here, like two. Now the model, feature-based content model is doing good. Where there is structure, very close by. But the experimental masking map, all of the subjects were the same. And there is an example, the equals method, we have lower distortion visibility over here, we have some lower distortion visibility over here, the information model will fail. Same model, actually, I would say it's really very good to actually have the similar pattern or similar pattern compared to the experimental masking map. So what can we do to have a better model to put the recognition effects within the model of the second model? So you see that our gain control model, we assume that the total model is based on the real simple set. That means that we are just modeling this specific back part of our brain. So like coming on with the GM and using the back of our brain, the V1, then other cortices which we have other high-level cortices coming on. Where in terms of modeling, we're just concerning about this one. But is it true that we definitely saw from our experiment and observation is not true? So we have to consider some other high-level cortices. Okay. So also from cognitive studies, using Arduino here and using one, we know that there is active feedback, but how to model these feedbacks so that we have a better model. So hypothesis was implemented definitely and used to have better intercortical or intercortical model or feedbacks and used to have better massing model or better distortion distribution. Now to have to introduce these feedbacks, intra and intercortical feedback within the masking model, I chose a two-stage model. First is to determine within the image if the structure is important for having a different distortion visibility than a regular masking model would produce. That's the previous two models. And if the structure is important, you think we are going to do something else to make the structural effect.
Structure recognition. Higher level.
Higher level. Yes. So that I showed you over here. In E2, we are probably forming a recognition of pages. Not recognition of pages. Probably. Yeah. V1 to V2. V2 will probably have some control integration. We'll have that. And higher level colleges will have some structural forming. So that cortices will have, we know that there is effect. We know that there is feedback coming from those cortices to V1, but how to model it? There's a challenge. So, this is the three-stage model that I was interested. And my proposition is something like this. So if we have a region which is devoid of structure, or devoid of structure, there is some gases over there, but it's not because we don't have the structure. We have, for example, neuron is fine, I'm showing you as a plus sign. It will have, from the high level cortices, we have higher neural distribution, so there is no structure. So higher level cortices is saying that if there is no structure, the distortion that we put within the image is not so important that we put within the region where we do have a structure. So if we have a structure, we have different inhibition other than the region where we have a structure. So that's my.
So is that related to the frequency? So the higher level frequency is the real high frequency signal?
No.
Similar structure?
Not frequency. Not going to be frequency. Say, for example, if we have a phase, now our, for example, V2 or V0 before, where the phases information is occurring, that information will go to the V1 and tells the V1 that, well, there is a structure over here. Now the inhibition of a single cell within the V1 will be different. Will be less.
I don't think it would be less. Certainly different, but what makes you think that there being a higher level structure would make the inhibition less?
The reason is that if the inhibition is less, then, that comes from the equation. It comes from the equation.